Hello Calc 3, welcome back to another video. In this video we are going to be finishing up section 13.1 and specifically we'll be talking about derivatives of vector valued functions. So remember that in the last video we developed the concept of a vector valued function and then we developed the concept of a limit of a vector valued function and then continuity of a vector valued function. And here we're going to continue mimicking the steps by which we developed calculus in Calc 1 and define the derivative for vector valued functions. So suppose that we have a vector valued function r and it's equal to f of t I plus g of t j plus h of t k, and this gives us the position vector of a particle moving along a curve in space, as we supposed in the last video, where f of t, g of t, and h of t are all differentiable functions. So remember that f of t, g of t, and h of t are just regular real-valued scalar functions, and they are differentiable. We know what that means. And let t be some time, and let delta t represent the change in time, some change in time, whatever it might be. Then the change in the position vector is going to be given by the position vector at t plus delta t and the position vector, or minus the position vector at t. Again, this should closely resemble how we started developing the derivative for regular real-valued functions. If you look over at this first diagram here, you can see our vector r of t plus delta t, which is the vector from the origin to q. We have our vector r of t going from the origin to p. And then you can see that there's a secant line being drawn between the point p and q. And in developing the derivative, we're going to see what happens as q gets closer and closer to our position vector r of t. So going back over to the left now, if we take delta r and we write it in component form now, all of our component functions are now written down, and we can combine them in such a way that the change in r is equal to f of t plus delta t minus f of t I, so that would be the I component. And then similar things happen for our scalar function g for the j component and our scalar function h for the k component. And now you should be recognizing that each of the components here are described by a scalar function, and this f of t plus delta t minus f of t looks awfully familiar to the difference quotient that we used in Calc 1 to define the derivative. And this is going to end up being quite important. So as delta t approaches 0, we want to see what happens in our diagram here to the right. So as delta t approaches 0, notice that the vector r of t plus delta t is going to get closer and closer and closer to our vector r of t. And q is going to get closer and closer to p, and the secant line, or in this case maybe we should call it a secant vector, something like that, but the secant line or vector or whatever is going to get closer and closer to a tangent line to the point P, which again is very similar to what happened when we defined the derivative for scalar functions. So, and probably the most important thing now to take away is what happens here as delta t starts going to 0. So remember that when we take the limit of a vector valued function, we take the limit of all of the components of the function. So if we take the limit as delta t goes to 0 of delta r over delta t, we get the limit as delta t goes to 0 of the difference quotient for our component function f. And in the j component, we get the limit as delta t goes to 0 for the difference quotient of our component function g. And for the k component, the same thing happens, but for the component function h. And now, we ultimately find that the limit as delta t goes to 0 of delta r over delta t is equal to the derivative of f with respect to t, that's the ith component, and then the derivative of g with respect to t is the j component, and the derivative of h with respect to t is the k component. So ultimately what this is telling us is that we are going to define the derivative with this difference quotient right here, and we're going to take the limit as delta t goes to 0, and ultimately the derivative is going to be equivalent to taking the derivative of each of the component functions that compose our vector valued function. So let's write that explicitly here. This is going to be the definition of the derivative for a vector valued function. So if we have a vector valued function r of t equals f of t I plus g of t j plus h of t k, it has a derivative at t if each of our component functions has a derivative at t. And if this is the case, then the derivative of our function r of t is denoted r prime of t, or dr dt, and it equals the limit as delta t goes to 0 of r of t plus delta t minus r of t all over delta t. And this is going to equal the derivative of all of the component functions. So again, what this tells us is that if we want to take the derivative of a vector valued function, then all we have to do is take the derivative of each of the component functions. That's really nice. So here are just a couple more definitions to be aware of. A vector function r is differentiable if it is differentiable at every point of its domain. And secondly, maybe the more unique one for vector valued functions, a curve traced by a vector function r is smooth if the derivative is continuous and never equal to the 0 vector. Okay, let's see what else we have here. The vector, if you go back up to our second diagram here, the vector r prime of t is going to be tangent to the point P in our diagram. So that's going to be called the tangent vector to the curve at P. And the tangent line to the curve at P is going to be the line that passes through P and is parallel to our tangent vector, r prime of t. So remember that to specify a line in space, we need two things. We need a point on the line, and we need a vector that the line is parallel to. Well, the tangent vector is going to be the vector our line is parallel to, and the point P will be the point on the line. So we can define the line with just the point P and the tangent vector. And lastly, the derivative, dr dt, if we're viewing the curve as being traced by a particle, the derivative dr dt is the rate of change of position with respect to time. And it's always going to point in the direction of motion of the particle, where again the particle is tracing the curve in space. So let's move on to some other definitions that are also related to the derivative. So if we have a position vector r representing a particle that's moving along a smooth curve in space, then the velocity of the particle is the derivative of the position of the particle. Okay, so the velocity function is also going to be a vector valued function, and it's given by the derivative of our position vector with respect to t. Speed, or the speed of the particle, is defined to be the magnitude of the velocity. So speed is going to be the length of the velocity vector. And again, this is going to end up being a function in terms of t. So we're going to put in values of t representing time, and it'll give us the speed of the particle at those different times. As you might expect, acceleration is going to be the derivative of the velocity function. And lastly, the unit vector that we get when we take the velocity function and divide it by the speed function will give us the direction of motion at time t. So here we're basically just taking away the magnitude of the velocity, and we're only worried about the direction the particle is moving in, and that's going to be called the direction of motion of the particle at different times t. All right, let's move into an example. So say we want to find the velocity and the speed of a particle whose motion is given by the vector function r of t is equal to 2 cosine ti plus 2 sine tj plus 5 cosine squared tk. Okay, so as we just defined, the velocity function will be given by taking the derivative of r with respect to t. And to find the derivative of r with respect to t, we just take the derivative of each of the components. So the derivative of 2 cosine t is negative 2 sine t. The derivative of 2 sine t is 2 cosine t. And the derivative of 5 cosine squared t will give us a negative 10 cosine t times sine t. So that'll give us our velocity function. And notice that it is a vector valued function, so you would put in the time t and it will give you a velocity vector. The speed, on the other hand, is not going to be a vector valued function. This is going to be a scalar function because you stick in a value for t, and because we're evaluating a magnitude, the function is going to give back a real number as opposed to a vector. So again, speed is defined to be the magnitude of the velocity vector at t. So we take the velocity vector that we just found and we calculate the magnitude by squaring each of the components and then taking the square root of their sum. And we do some algebra here, but eventually we get down to this answer here. So the function for speed in terms of t could be given by 2 times the square root of 1 plus 25 times cosine squared of t times sine squared of t. And this is a little bit different than the book's answer. I think the book, when they got this up here as the k component for the velocity function, used a trig identity to simplify that, and it made their speed function a little bit simpler. But the answer should be equivalent to whatever the book has. Okay, so now that we have a good grasp on what the derivative of a vector function is, let's create some rules for differentiation, or maybe I shouldn't say create, let's derive some rules for differentiation, or at least list them. So if we let u and v be vector functions, and we let big C be some constant vector, and we let little c be some scalar, we let f of t be a differentiable scalar function. So f of t is going to take in real values and output real values. Then we have the following rules of differentiation. These rules are listed in your book. I just listed them here for your convenience, if that's more convenient for you. If not, you can just use your book. I do want to mention each of them. The book gives 3 proofs for, I think, just the dot product rule, the cross product rule, and the chain rule. I'm going to give a proof of the sum rule down here, but you can check out the proofs that the book gives if you want to. If you're not interested, it's fine for you to just know the rules and be able to use them. But let's start off with the first one, the constant function rule. So if we have a constant vector in this case, and we want to take the derivative with respect to t, we get the 0 vector. So that's something that we would probably expect. A couple of scalar multiple rules. So if we have the scalar c being multiplied by a vector function u, and we want to take the derivative of the whole thing, we can just pull the scalar out. That's nice. Also resembling the fact that we can pull scalar multiples out of derivatives when we are differentiating regular real valued functions. Also, if we have a scalar function as opposed to just a scalar constant being multiplied by a vector function u, then we end up with something that looks like the product rule when we take the derivative. So we end up with the derivative of f of t times u of t plus f of t times the derivative of u of t. And we're going to see that pattern multiple times below. The sum rule is exactly what you would expect. So the derivative of the sum of two vector valued functions is equal to the derivative, or the sum of the derivative of each function. The difference rule is likewise. So if you have the difference of two vector valued functions, that's going to equal the difference of the derivatives of each of the functions. So u prime of t minus v prime of t. And here are some more interesting rules that have to do with just vector valued functions, where we can actually define things like the dot product and the cross product, but both of them will have the same format as the product rule that we should be familiar with. So if we have two vectors, we take the derivative of them when they're being when we're taking the dot product of the two vectors. Then we end up with the derivative of the first dot producted with the second, and then plus the dot product of the first and the derivative of the second. And for the cross product rule, looks very similar. So here we're taking the derivative of the cross product of two vectors. We end up with u prime of t, the cross product with v of t, plus u of t, the cross product with v prime of t. So both of these rules just mimic the regular product rules for real valued functions. And then finally, the chain rule is also going to look very similar to the chain rule that we saw in Calc 1. So if I can write a vector valued function as u of f of t, where f of t is not a vector valued function, it's a scalar function, then the derivative of u of f of t will equal the derivative of that inner scalar function, so f prime of t, multiplied by the derivative of our vector function u evaluated at f of t. So again, that should look very similar to the chain rule from Calc 1. And I'm going to give a little bit of a proof of the sum rule. It shouldn't be too long. So we want to take the derivative of u of t plus v of t, and to do that I'm just going to expand and use the component forms of both of our vector functions here. So we end up with the derivative with respect to t of u1 of t plus v1 of t, and the derivative with respect to t of u2 of t plus v2 of t, that's the j component here. And then the k component is going to be the derivative of u3 of t plus v3 of t. And now we can just apply the sum rule for derivatives of real valued functions. So the derivative of u1 of t plus v1 of t is going to be the same as u1 prime of t plus v1 prime of t. And the same can be said for what's going on in our other components here. So we get u2 prime of t plus v2 prime of t, and u3 prime of t plus v3 prime of t for each of our components now. And now we can make things look a little bit nicer. So we group all of our u components together, and we get a u1 prime of ti plus u2 prime of tj plus u3 prime of tk. And then the same thing for all of our v components over here. And of course, we can rewrite that as just u prime of t plus v prime of t, since u1, u2, and u3 are the component functions of u. Okay, and as I said before, the proof of the dot product, the cross product, and the chain rule, all of those rules are given in the book. I don't want to put them here, it's just a little bit too lengthy. And finally, just this last tidbit. So let's talk about vector functions where the position vector always has a constant length, because some interesting things happen in this case. And they're going to show up again when we get to section 13.4. So assume that we have a vector valued function r, and the magnitude of r of t is always equal to c, regardless of what value of t we stick in for r. We always get a magnitude of c, where c is just some constant. So an example of such a vector valued function would be any vector valued function that traces out a curve lying on a sphere, right? Because if it's tracing out a curve on a sphere, then each of the points on the curve is going to have the same distance from the origin. So the magnitude of all of the position vectors are going to be the same. So if this is the case, remember that we can take the dot product of two vectors, or the dot product of a vector with itself, and that's going to give us the magnitude of the vector squared. And we assume that the magnitude of the vector is always equal to c, so that'll equal c squared for all t. So r of t, or the dot product of r of t with r of t, is going to be equal to c squared for all t. And now we can take the derivative of both sides of that equation. The derivative of the left side, we're going to use the dot product rule, which we just listed. So it mimics the product rule. And on the right side of the equation, this derivative of c squared is going to equal 0 because we're just taking the derivative of a constant. And we end up with the dot product of r of t with r prime of t plus the dot product of r prime of t with r of t is equal to 0. We can combine both of these and get 2 times the dot product of r of t with r prime of t is equal to 0. Divide both sides of the equation by 2, and we're just left with the dot product of r of t and r prime of t is equal to 0. And remember from section 12.3, when we talked about the dot product, if we have two vectors and we take their dot product and it gives us 0, then those two vectors are going to be orthogonal. And if they're non-zero vectors, it means that the vectors are perpendicular. So, again, this implies that if we have a vector function and the magnitude of the vector is always equal to c, regardless of what we stick in for t, then r prime of t and r of t will always be orthogonal. Okay, so that is the end of the material for section 13.1. Material for section 13.2 should be coming up shortly.